Okay, so osmotic pressure is a colligative property, right? So, and we have here, osmotic pressure is equal I times mole divided by volume of the solution. Volumes need to be in liters, times R. R, it is universal gas constant, T, temperature. So, what is this portion here? Moles over volume, it's molarity. Molarity, right? So that means you can say osmotic pressure is equal to the I, que es Van Hoff factor, times molarity, times universal gas constant, times temperature. And we have here, if two solutions separated by a semi-permeable membrane have the same osmotic pressure. So if they have the same osmotic pressure, no osmosis will happen. And then types of solutions and osmosis. Isotonic solutions, that means the same osmotic pressure. The solvent passes the membrane at the same rate in both the same ways, right? If you have a hypotonic solution, lower osmotic pressure, that means the solvent will leave the solution at a higher rate than it enters with. And if you have a hypertonic solution, higher osmotic pressure, so that means it will have a higher osmotic pressure, so solvent will enter the solution at a higher rate than it leaves with. So problem 3 here. The osmotic pressure of an aqueous solution of a certain protein was measured to find the protein's molar mass. So the solution contained 3.50 milligrams of protein dissolved in sufficient water to form 5 milliliters of solution. Then the osmotic pressure of solution at 25 degrees Celsius was found to be 1.154 torr. So treating the protein as a non-electrolyte, calculate its molar mass. Now, so let's start with osmotic pressure formula. We just saw here, right? Osmotic pressure is equal to I times molarity times R times T. So let's go ahead here. Times T. So osmotic pressure was given to be 1.50 torr, 1.54 torr, right? So let's see what we have initially here. The I for non-electrolyte is equal to 1. Because we'll just, for non-electrolyte, you dissolve it just as one particle. So 1 for I. Molarity is what you need to find here. R, universal gas constant, let's be, the R is a constant, right? We have different R's, but let's use one in ATM. ATM per liter mole Kelvin, right? Times 0.08206 ATM liters per mole Kelvin times T. T is temperature, was given in Celsius. So our R is ATM liters per mole Kelvin. So let's keep it all the same temperature, sorry, all the temperature in the same units. So 25 plus 273 is equal to 298 Kelvin, right? So times to 298 Kelvin. Okay, but what the osmotic pressure? The osmotic pressure was given in torr, but our R here is in ATM, so let's go ahead and convert it from torr to ATM, right? So 1.54 torr times, so for each 1 ATM, you have 760 torr. So how much are going to be this division here? 1.50 torr, 1.54 divided by 760, it will be 2.0263 times 10 to the minus 3 ATM, right? So now let's go ahead here. So your osmotic pressure will be 2.0263 times 10 to the minus 3 ATM. So let's rearrange it here because you want to find the only variable that you do not have here, the only parameter that you don't have here is molarity, right? So everything you have here, so molarity is your unknown, right? So, and everything that is heavy here, let's rearrange it, and then we're going to be dividing here, right? 1 times 0.08206 times 298 Kelvin. So how much is going to be your molarity here? Divided by, so it will be this, the atmospheric pressure, sorry, the osmotic pressure, right? Divided by the, divided by all this thing here, 0.08206 times 298. So your molarity is going to be 8.206 times 10 to the minus 5 molar. So the units here will be 80 milliliters per mole Kelvin. When you cancel out everything, you cancel ATM with ATM, Kelvin with Kelvin. The only unit left will be mole and liter, right? That's molarity here. Now, you have the molarity here. What's molarity formula? Molarity is equal to moles of solute divided by the volume of the solvent in liters. Sorry, the volume of solution in liters. So let's see what you have here. What the question gave it to us. You just found the molarity, right? And what's the volume given here? The solution has 5 milliliters of solution. Go from 5 milliliters to volume of solution liters. So just convert to liters. You know that it's 1 liter. You have 1,000 milliliters, right? So we're going to be to the minus 3 liters. So to calculate the moles, you multiply molarity times volume, right? We're going to rearrange it here. You'll be moles of solute is equal to, remember, this is just simple algebra, just like if you You're going to be working here, divide by what you want to find. And let's go ahead here. Moles will be multiplication between molarity and volume. Volume, so molarity is 80.286 times 10 to the minus 5 times the volume is here, right? 5 to the minus 3. I not put the unit just because there is no room here, but if you put the unit here, remember they're going to be canceling mole per liter with liters, so the left unit going to be moles. So 8.286 exponential to the minus 5 times 10 to the minus 5, right? Times 5 to the minus 3 will be 4.143 to the minus 7 moles, right? So the question is asking for molar mass. Now you found it moles. So remember, the first step here was to calculate, to use the osmotic pressure to calculate the molarity, right? Here was the first step to calculate the molarity. After you find molarity, you're going to use this formation to calculate your moles. Now let's go to the third step, step 3. Using moles number in the mass of the solute given, let's calculate the molar mass. So moles, it is mass divided by molar mass. What was? So let's rearrange it here. Molar mass will be equal to mass divided by number of moles. So the mass given was 3.50 milligrams, but you needed to use in grams per mole, because grams per mole, you're going to be using grams because the molar mass will be in grams per mole. So this is why I need to convert milligrams of solute here to the grams of solute. So let's just find it here a little bit. I'm sorry, I'm using the page here. So 3.50 milligrams. You know that 1 gram, you have 1,000 milligrams, right? Cancel milligrams with milligrams. So you have it here when you calculated 3.50 divided by 1,000 will be 3.50 times 10 to the minus 3 grams. So let's take it. 3.50 times 10 to the minus 3 grams divided by the moles. 4.143 times 10 to the minus 7 moles. 3.50 exponential to the minus 3 divided by 4.143 exponential to the minus 7. So it will be, the molar mass will be 8,000 like 44.7 like grams per mole. But we want to do to this, let this answer only 3 significant figures, right? 1, 2, 3, 1, 2, 3. Let's let everything in 3 significant figures. So the molar mass is equal to 8.5, sorry, 8.45, right? Because we're gonna round this to 5 here, times 10 to the third grams per mole. That's exactly what you have here as answer, right? Now, so a little bit of a theory here. Oops. Osmosis and blood cells. Red blood cells have semi-permeable membranes. If stored in hypertonic solution, they will shrivel as water leaves the cell. That's called crenation. So, crenation here. The crenation of a blood cell placed like in a hypertonic solution. So if solution here is hypertonic, the water will be leaving the cell. Are you seeing here the water leaving the cell? So the cell will have a crenation. If you have a blood cell stored in a hypotonic solution, that means the outside is lower solute concentration, the environment here. So you have in the side you have a high solute concentration. So it's going to be happening here. Will happen here because the water will be growing inside the cell, going to inside the cell until they burst. So will be hemolysis here. So hemolysis of a red blood cell is placed in hypotonic solution. So hypotonic solution environment is why the environment has a lower concentration. If you have a hypertonic solutions when the environment has a higher concentration. So what's the ideal? So in intravenous solution, you needed to work with isotonic solution. So the solution must be isotonic to the blood, So that means should have the same concentration, right? Because you don't want to happen crenation, don't happen the opposite, right? So here's this last page for chapter 13, talking a little bit of colloids. Suspension of particles larger than individual ions molecules. So the colloids have suspension of particles larger than individual ions or molecules, but too small to be set out by gravity. So they are called colloids. So colloids are formed by is between solutions and suspensions. And I have here some examples. For example, if you have the phase of colloid, a gas, and dispersing solvent-like is a gas, and then dispersed solute-like substance, you have a solid, you have the colloid type is called aerosol. That example have a smoke. So smoke, you have phase gas, phase of colloid is a gas, dispersing phase is also gas, but if dispersed is the solute. So it's called smoke. Is we have example as smoke. If you have, for example, here, the liquid as the phase of colloid, as dispersing, that's this dispersing substance is a liquid. and the solute is also liquid, you have your emulsion, the colloidal time emulsion, and you have example, you have a milk. Colloids in the biomolecules. Some molecules have a polar side, polar ending, and non-polar ending. So they are so large, they are large molecules. Some molecules that have it, so they have a hydrophilic and hydrophobic. So hydrophilic is the polar ending, because the hydrophilic is water loving, right? Remember the sentence like it dissolves like, because they mean they have the same polarity. They will be dissolving each other. They'll be mixing, dissolving each other. So hydrophilic, that means water loving. If the other side, the other end is a non-polar, you have a hydrophobic. Phobic means fearing, hating, right? And that means hydros means water. So hydrophobic means water fearing ending. So large molecules that form colloids in water often had hydrophilic portion face outward to interact with the water. Hydrophilic is what? Water loving, right? So this side here, the water loving, you'll be interacting, you'll be facing outward to interact with the water. So colloids can aid in the emulsification of fats and oils in aqueous solutions. In an emulsifier causes something that normally does not dissolve in a solvent to do so. Because so we have here two endings, right? Okay. Now, so we have here hydrophobic ending, hydrophilic ending, and remember the hydrophilic means hydrophilic will be interacting with the water, because like dissolves like. Okay, let me stop here, chapter 13.